Today I'm going to talk about number systems and their properties. This is in day 1 of your notes. So a lot of what I'm going to talk about today is review, but I'm going to formalize it a little bit and help you remember some things. There are different number systems. At the top of this flow chart are complex numbers. Complex numbers have a real component and an imaginary component. Real numbers are all the numbers that you can think of on the number line. They include fractions, they include decimals, they include numbers like pi. An imaginary number is the square root of -1, which is I. And a complex number combines a real number with an imaginary number, and it looks something like this. We'll talk more about complex numbers throughout this course. Within real numbers, we have rational numbers and irrational numbers. Rational numbers are numbers that can be written as a fraction where a and b are both integers. Not all real numbers can be written as a fraction. Those include numbers like square root of 3, non-reducible radicals are irrational. If you were to put that into your calculator, you would see that it is a decimal, but there really is not a pattern to the decimal. Numbers like pi is irrational. A number like this so this has a pattern, but every single time I go out, I repeat it by one more zero. When I'm looking at a rational number, you can have a repeating decimal like 0.3 repeating, that's 1/3, or 0.125. As long as there's a periodic repeating decimal, it is rational and you can write it as a fraction. Within rational numbers, we have whole numbers. Whole numbers are numbers, counting numbers, including 0. We have integers. Integers are negative numbers and positive numbers without decimals. So like -3, -2, -1, 0, 1, 2, 3. Those are integers. We typically abbreviate the type of numbers that are integers with a capital letter Z. We abbreviate whole numbers with a capital W. We abbreviate real numbers with an R. We abbreviate rational numbers with a Q, which stands for quotient. Irrational numbers, I'm not quite sure what we use. I generally will write out irrational. And then one more set of numbers within the rational number system are the natural numbers. Ooh, misspelled that. Let's go back. Natural numbers. And these are the counting numbers. So whole numbers include natural numbers. Whole numbers include natural numbers except they have a 0 in them, in that set. And I remember whole numbers have the 0 because 0 is a whole. And then everything else I just have to remember somehow, some way. What our flow chart looked like. If a number is a rational number, it is a real number. Yes, that's true. And it's always. Now I would like to look at these true-false questions. And I'm going to do one with you, and then I'm going to have you do the other two. So it says, determine if the following statements are true or false, then write the converse of the statement and determine if the converse of the statement is true or false. Remember, the converse of a statement, of an if-then statement, you get by switching the if and the then part. So first we're going to look at this first statement. If a number is a rational number, then it is a real number. And this has to be true for every single rational number that's out there. Now, if you remember, it's true. Now I'm going to write the converse of that statement. If a number is a real number, then it is rational. Now, a number that, like the number 2, is a real number and it is rational, but this is still, I forgot the F. But this is still a false statement, because if I can find one case that makes this statement untrue, then the whole statement is false. So what I would choose is pi. Pi is a real number, but is not rational. And that's what you call a counterexample. And that is a false statement. Now I'd like you to pause your video and finish the next two problems. When you are done and ready to see the answer, press play again. Here are the answers to the next two problems. Number 2, if a number is a real number, then it is a rational number. And that's actually the converse of number 1, that's false. And the converse of number 2 is if a number is rational, then it is real, that's true. Number 3, if a number is an integer, then it is a whole number. That's false, because 0 is an integer and it is not a whole number. -1 is an integer and it's not a whole number, so it's false. The converse of that is if a number is a whole number, then it is an integer. Now that is true. A number that's a whole number is an integer. All whole numbers are integers. So next I want to talk about some properties of real numbers. These are all properties of real numbers. So the closure property says a set of numbers is closed over an operation if, when the operation is performed on any two elements in the set, the result also belongs to the set. So for example, 1 and 2 are real numbers. If I added 1 and 2, I would get another real number. So if I could think of two numbers that I could add together, two real numbers, when added together, and my result is not real, then I would say it's not closed. But since for all numbers, all real numbers that I add together that are real numbers, becomes a real number, the results are always real, then the real numbers have the closure property under addition. So let's look at part A. We're going to determine what if the following sets of numbers are closed under the indicate operation or not. We're going to give the reason for our answer, and if the closure property does not apply for a given set of numbers for the indicate operation, we're going to provide a counterexample. So let's look at part A. Part A says negative integers for addition. So let's see. That's my set of numbers. And the question is, if I always add two negative numbers, do I get a negative number out? So I can't think of any two numbers that I could add together and not get a negative integer. So this is closed under addition. Now let's look at part B. Part B says negative integers, that's my set for multiplication. Well, if I multiply -1 times -2, I get a positive number, which is not a negative integer. So this, Oh, something bad happened. So this does not have the closure property. And this is my counterexample. Now, press pause on your video, do the last two problems on this page, and when you are ready to see the answer, press play again. So, positive integers for subtraction is not closed. My counterexample was 2 minus 4 equals negative 2. So I took two positive numbers. Those positive numbers were 2 and 4. I subtracted them, and I got a negative number, which is not in the set of positive integers, so it is not closed. However, whole numbers for addition is closed. The next property that I'd like to talk about is the commutative property. I'm sure you've heard of this one before. If you change the order with an operation, you get the same results. So the operation star, in this case, is commutative on a set of numbers if and only if for all numbers in the set. A star B equals B star A, so I can rearrange them. Now we have to look at each of these and decide whether or not they demonstrate the commutative property. If an equation does not demonstrate the commutative property, we're going to explain why. Well, in part A, you'll notice I'm not just changing the order around an operation, so this does not. Wait, yes it does. So here's a number, here's a number. I switched the order, and you can see that they are equal. So I'd have 8 plus 2 equals 2 plus 8. And that is true. 10 is equal to 10. Now, I would like you to look at the last three problems on this page. Press pause on your video, do your answers, and then press play to check your results. So part B does not show the commutative property because I have 5 plus 8 plus 3, and you notice that I'm changing the order of things. So I just switched here the parentheses. The order does not change, the parentheses do. So that does not show the commutative property. With commutative property, you change the orders of the numbers. In part C, this does not show the commutative property. You'll notice I have 9 divided by 3 plus 2. I just switched the order of the 9 and the 3, and it absolutely does not work. That does not show the commutative property. Part D does show the commutative property. I changed the order here. I switched the 3 with the 2x minus 4. So the 3 moved to the back end, the 2x minus 4 moved to the front, and you'll notice no matter what you put in for x, it will absolutely be true. So that does show the commutative property. The next property I'd like to talk about is the associative property. An operation star is associative over a set of numbers if and only if for all numbers in the set. When we switch the parentheses around, we keep the order exactly the same, but we switch the parentheses around, we get the same result. So now I would like you to take a look at A, B, C, and D, decide whether or not they show the associative property. And if equation does not demonstrate the associative property, I want you to explain why. Press pause on your video. When you're ready to check your answers, press play again. And here are my answers. The first letter A does not show the associative property. I changed, it was 5 minus 2x plus 4, and we just switched the parentheses to move the parentheses around the 5 and the 2x rather than the 2x plus 4, and you'll notice that they don't work. The operations are mixed. I have some subtraction and some addition. That does not work. Part B does show the associative property. The order of the elements are all the same. I just have switched the parentheses around. Part C does show the associative property. The order is the same. The parentheses are switched. Part D, this does not show the associative property. The order is different and the elements are not regrouped. The next property is the distributive property. An operation star is distributive over a second operation plus, if and only if, for all numbers in the set, A times A star, the quantity, equals A star B plus A star C. So we're distributing the A over the parentheses. So again, we're supposed to look here. It says simplify each of the following expressions to expressions by applying the distributive property and combining like terms. If the distributive property cannot be applied, explain why. Press pause on your video feed and try to do these problems. When you're ready to see the answers, press play again. So here are my solutions. Part A, I distributed the 3 over the 2x minus 4, and here, remember, you have to also distribute the negative. So I have a negative 3x and then plus 6y. I combined like terms. In part B, same idea. I distributed 3 over the 5 minus w, and now here I distributed the negative over w minus 3. So I have the negative w plus 3. That works. Same thing for part C. I distributed the 5, and then I distributed the negative 2. Part D, the distributive property is not used here. Multiplication is not distributive over itself. However, the expression may be simplified, which is what I did. You don't distribute 3 to the 2 and to the w. You just simply multiply out. There are several properties that go along with real numbers and all the different operations. I have them printed out for you on your sheet. And you can see the inverse property of addition. If the sum of two numbers is 0, then they are additive inverses. For example, a plus negative a is 0. A and negative a are additive inverses of each other. Inverse property of multiplication. If the product of two numbers is 1, then they are multiplicative inverses. For example, a times 1 over a is 1. A and 1 over a are multiplicative inverses of each other. The identity property of addition says a number that, when added to all other elements of the number set, leaves the other number unchanged. So 0 is the identity element for addition. If I add 0 to any other number, any other real number, I get that number out. That's the identity operation for identity property for addition. Identity property for multiplication says basically the same thing. I want a number to use to multiply by any other number to get that same number out. It's a number that, when multiplied by all other elements of the number set, leaves the other number unchanged. So here's what that means. 1 is the identity element for multiplication. A times 1 is A. No matter what real number I take, multiplied by 1, I get that same number out. Substitution property of equality says that if A equals B, then B may be substituted for A in algebraic expressions. So for example, if A is equal to B, and I have A plus 2 plus Z, I can put B in for A, and I get B plus 2 plus Z. Now we're going to identify what property is used in each of these steps. Press pause on your video feed, give it your best shot. When you're ready to see the answers, press play again. Okay. In my first step, what was used was the distributive property. You'll notice the 3 was distributed over the 3 minus 2x to get 9 minus 6x. Then I distributed the negative 4 over x minus 5. It's negative 4x plus 20. And then we still had the 11x minus 29. In the next step, it used the commutative property. And all that happened here is I switched the order around so that I could add my like terms. The next property is the distributive property in reverse. This distributed the x out. Then the next property is the substitution property. I substituted 1 for negative 6 minus 4 plus 11. And I substituted it in 0 for 9 plus 20 minus 29. My next step is the identity property of addition. 0 plus any real number gives me the number back. And the next property is the identity property of multiplication. Now, no one would solve an equation or an expression or simplify an expression using that many steps. But it's really good to see what's going on and how these properties apply. Okay, in this next screen, we want to evaluate the algebraic expressions with various values for x in the variables. So we're going to substitute in the value given, and then we're going to simplify. And you'll notice at the end, we want to explain why the values that we got in the first process above should equal the values that you got in the second process. So we're using this expression here, and we're using this expression there. I want you to press pause, give this a shot. When you're ready for the answers again, press play. Okay, so here are my answers. I took negative 1 and I put it in for x, and I got 6. I put in 2 for a and negative 3 for b, and simplified, and I got 4. The next part says we're going to simplify the expression algebraically and then substitute in negative 1. So I simplified 5 times the quantity 2 minus x plus 3x minus 6. I first distributed, and then I combined like terms, and then I evaluated. I got the same answer. Same idea here. I simplified, then I plugged in the same value, I got the same answer. The reason this works is that algebraic properties are appropriate and produce the same results. That is my lesson for today. Have a great day. Your homework is posted online. See you soon.